Okay, so moving on from using a table to just looking at word problems, there's different phrasing that you just have to make sure that you're paying attention to. So what is the probability of having rolled a 5 on a number cube labeled 1 through 6 if you know that you rolled an odd number? So I'm going to list out the sample space here. And I know I rolled an odd number. So those are the only options that I can come from. So my sample space then is limited. So what's the probability of rolling a 5? Knowing that I rolled an odd, there's a 1 in 3 chance. Terry has a number cube that's labeled 1 through 6. He rolls the cube twice. What's the probability that the sum of the two rolls is an even number, given that the roll is first a 3? So what you're actually going to have to do here is you're going to have to look up that 9.1 lattice that we had for when we listed out the sample space for the how odd task. So given that the first roll is a 3, there are 6 different options that we could have. So we have, I'm just going to list them all: 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. So that's the condition. So when I roll a dice, there's 36 outcomes. If I roll 2 dice, because it has to be a 3 first, then that limits the outcomes to 6. So what's the probability that he rolls a sum is an even number? So the sum here is an even. So 4, here is an even, and here is an even. So that's going to be 3 out of 6. Okay, consider a bag with marbles, 3 blue marbles. I love drawing the little marbles in their colors. I just think it helps me visualize what's going on a little bit easier. So here's all my marbles for a total of 10 marbles. What is the probability of picking green given that the first pick was green? So we're picking out 2 marbles and we're not putting it back. So when we don't put it back, we're changing that denominator again. So given that the first pick was a green, okay, but I've already picked 1 green, 1 out. Okay, what's the probability of picking a green? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be 4 out of 9. So there's 4 green ones left because I already picked out one of the greens, and then you have your remaining. What's the probability of picking a blue given that the first pick was red? So I'm going to simulate that again. So we're now in this case we picked a red one first. So I'm going to cross out the red one. Oops, that's supposed to be green. Cross out the red one. So I know I picked a red one. What's the probability that the pick will be blue? So there's 3 blue ones out of 9. So that denominator is what changes. And it's easy to identify the sample space and to list it out, and then to kind of think about what the scenario is going through. But there's also another way to do this, and it's using a conditional probability formula. So here is the formula for conditional probability. The probability of A given B, so everything that's given is always going to be the second half, or the second letter. And what you're going to do is you're going to take the probability of A and B, and the notation for A and B is A, a little upside down U, and B, divided by B. So the probability that a cat in the shelter is black is, so the probability of a black cat is 0.73. The probability that the cat is black and has short hair, so short and black cat, is 0.64. What's the probability the cat has short hair given that the cat is black? So that's going to be the probability of short hair and black over the probability that it's a black cat. So the given condition is always what you're dividing by. So then I already have those data values for you. So all you're doing is you're taking 0.64 dividing by 0.73. And in fact, if you were to reverse these answers around, you would get an error, or you would get a number that's bigger than 1. But we know that probability cannot be bigger than 1 because probability cannot exceed 100%. So that's going to be 0.8767. Okay, and that is your conditional probability. So now we're moving on to independent events, so proving that something is independent. There are 2 different ways that we can prove independence. The first is by this formula. If these two values equal exactly when you multiply them, that means they're independent. So if I multiply the probability of A times the probability of B, and it equals the intersection, that's going to be an independent event. You can also do the probability of A given B equals the probability of A and B. And that makes sense because if B has no effect on A, then when I divide by it, it wouldn't have any effect on the actual probability. So determine if it's independent or dependent. So I'm going to check probability of A times the probability of B. See what those two values are. So I'm going to multiply 0.25 times 0.25. And it has to equal 0.5 exactly. Well, when I multiply 0.25 times 0.25, that gives me 0.0625, which is nowhere near to 0.5, so that means it's dependent. Okay, and if I were to do the same thing for part B, if I multiply 0.8 times 0.4, that gives me 0.32, which is equal to the intersection, so therefore it's independent. Okay, and just one more example. I know this video is getting a little bit long, but one more example to go through is if we're using a two-way table and just figuring out those different probabilities. So the total we have is 60, so for most of these, the outcome will be 60 unless we're working with conditional probabilities. So the probability of basketball, that's going to be 38 out of 60. Probability of males is going to be, and I don't have those totals yet, so that's fun. I have to add all those together. So 40 plus 22 plus 15 is 77. Ooh, I actually need to go back from here too. I have to get those big totals there. So 77. And then we have 12 plus 16 plus 45, which is 73. So actually, this big total is 150, so that's the denominator for my first one. Sorry about that. Okay, probability of males, so how many total males there are? There's 77 out of 150. All right, and this is where we start to see those conditional probabilities. So probability of basketball, given that they're a male. So given that the student was a male, whoa, that is way too big. There we go. So given 77, that's the condition that's been set, so that's going to be my denominator. What is the probability that they play basketball? And there's 22 kids that played basketball. Okay, given, so let me erase this yellow part here. Given that they are playing basketball, so now this is my condition. So now my denominator is 38. What's the probability they are male? Which is 22. So this is the given condition. This is what it's asking for the probability of. This is the given condition. This is what it's asking for the probability of. Okay. Probability of football or basketball. So football is going to be 52 out of 150, or means add basketball, which is 38 out of 150. So you'll notice in this case, sometimes the or, if they're mutually inclusive, you have to subtract. But in this case, because football and basketball are separate, or like separate probabilities, you don't have to actually subtract. That's going to be a mutually exclusive event. So 52 plus 38 gives me 90 out of 150. And again, I want to leave that unsimplified because I want to represent all those 150 students. Okay, basketball and male. So basketball and male, find that intersection. It's going to be 22 out of 150.
Good afternoon, Seahawks. Hope everybody's having a good day.
And then female and baseball is going to be 45 out of 150.
J through M, you are now dismissed.
Sorry about the interruption there, but female and baseball is going to be 45 out of 150. Okay, so showing both methods, so both methods being that A and B, are they independent or not? So there's two ways that we can prove it. Are male and basketball independent? So probability of male, we can do times the probability of basketball, and we could say, is that equal to the probability of male and basketball? So that's the one way to prove it. And we can also say the probability of A given B, so that's my conditional probability statement, that second one, is that equal just to the probability of A? So is the probability of male given basketball equal to the probability of just male? So check those on your own. Typically when you have a table, you do have some overlap going on, so hopefully the answers that you're going to see is that they are not independent because neither of those two equations are satisfied. But give it a try. Let me know if you have any questions.